So hello and welcome to 451. This is Math 451, Probability, in the fall 2020 semester. So to start off today with our first lecture, first I'm going to go through some of the materials that I have assembled on the webpage and on Blackboard. So I'm going to kind of run through that quickly. I'm going to talk a little bit about the structure of the course, what we're going to be covering, grading, those fun topics. And then we're going to launch into kind of a background review of some set notation, which is going to kind of show up at the beginning of the course quite heavily. So here is our webpage for Math 451, gjhunt.github.io/math4512020. And so I have a couple things on the website currently. So I have a syllabus here. So I can click on syllabus. This will bring us to the kind of course syllabus. This is the syllabus. This is me, Dr. Hunt. That's my office, which is not super relevant this semester. And here's my email, which is going to be quite relevant. Office hours. Here's a link to my Zoom meeting room. So I'm going to have office hours Tuesday, kind of in the afternoon, 3:30 to 5 p.m. EST, and Wednesday in the morning, 9 to 10:30 EST. Alternatively, I'm happy to meet with people outside of that. So if those times don't work for you and you want to meet, send me an email at my email, drop me a line. We can make something work. So the textbook I have listed here is Dr. Lemus's book, Probability, the second edition, which is from 2018. Here's a link to Amazon where you can buy it. I have written that the text is kind of required for homework problems. I think theoretically, none of the graded assignments are going to need the book. That said, the book is quite good. Reading the book is very helpful. And there are going to be a lot of suggested problems that you're really going to need to do if you want to succeed in the course. And you will need the textbook for those, and I'm going to be referencing problem numbers from the second edition for that. So if you have a first edition, that's okay, but the problem number is going to be referenced from the second edition, which might be slightly different. I'm going to try and post some screenshots of the problems as we go along the course. So if you don't have the book yet, or don't have the right version, or might never have the book, that you can at least still kind of keep along with the suggested problems. Although I do recommend getting the book. It's a nice book and will really supplement my lectures and give you kind of different view of the same material. For the grade breakdown for the course, it's pretty simple. This is one of the higher level math courses offered at the college, and it's taught like many of the other kind of higher level math courses. So our graded problems, which we'll talk about in a little more detail, are going to be 20%. So it's kind of a homework proportion. Then we're going to have a midterm, which will be 40%, and then a final, which will be 40%. So the midterm right now are scheduled for Thursday, October 8th from 7 to 8:30 p.m. EST. So that's a night exam. We'll talk a little more in detail about that as we get closer to October 8th. It will cover kind of the first half of the course. And if you can't make that time, definitely, and you know that right now, you can reach out to me. But we'll hear a little bit more as we get into September about that midterm. The final, I don't have a date for yet. We're still working that date out, but hopefully in the next week or so, I'll have a final date, and I'll send out an announcement about that. So attendance, there's no real attendance policy. This is all remote and asynchronous. Hopefully the lectures are helpful for you, so you should listen to the lectures. You definitely have to show up to the midterm final exam. And you really need to do the graded problems. So you need to do the things that contribute to the percentage of the grade, but not really checking attendance or anything. And it's asynchronous, so that doesn't make a lot of sense anyways. So for the homework, I'll talk a little more in detail in a second about that. We're going to have basically a kind of homework problem due every week that I'll grade. You're just going to submit them on Blackboard. Don't need them, email them to me. Don't turn them in late. So that's kind of the syllabus, just a one-page syllabus. I have the course outline here. So this is a very tentative course outline, although I've taught this course several times before, so we're going to stick pretty close to this. Although I'm going to write here at the top, this is approximate, it can change. And so this is kind of approximately what we're going to do. The dates for the graded problems are pretty much set, though. So here I have the lecture number, the date, day of the week. So this is based on a 2 lecture a week course. I know it's remote asynchronous, and so every week I'm going to post 2 lectures, kind of corresponding to a Tuesday, Thursday. So this week we have our first introduction lecture, and I'm posting on a Thursday. The topic, sets, operations, partitions, etc. And I have the corresponding section of the book. I'm going to assign the quiz problem, which is the 1 graded problem today. That's actually already on Blackboard. That will be due next Thursday at midnight, so August 27th. Next week, we'll have lectures 2 and 3 that are posted, correspond to these topics. We'll have quiz problem 2, which will be assigned on Thursday and due the following Thursday. And that's pretty much how the course is going to go. So you have the dates of the kind of graded, what I'm calling quiz problems. The midterm date here on October 8th. And so we'll only have 1 lecture that week. And then at the end, we'll have some kind of final exam, date TBA. Okay, but that kind of gives you an outline of the topics and corresponding sections of the book, so you can kind of keep up along with that. So I have this welcome announcement here, which I had sent out as an announcement on Blackboard, which gives kind of much finer detail. So there's the website. There's a Blackboard website we'll look at in a second. My GitHub page here. So the course is remote asynchronous. On typically Mondays, going to post the 2 lectures of the week, kind of corresponding to a Tuesday, Thursday, 80 minutes, which is a typical lecture time. They're going to be posted here, which is the playlist on my YouTube channel for the fall 2020 semester. I'm also going to update it on, if I go back to the page here, I'll have this section of lecture notes and videos. So today, after I'm done recording this, I'll post the lecture 820, what it's about. Here I'll have a link to a PDF of the written notes. I'll have a link to the video on YouTube. This link goes to the playlist, which currently is going to be empty, if it loads. Yep, kind of an empty list so far. And then I'm going to post corresponding video lectures from Dr. Lemus's very nice lecture, recorded lectures. So this link takes you to his page with those recorded lectures. So this corresponds to the sections of the book, and he has, again, YouTube videos corresponding to the various sections. This is much more detail than I'm going to go into. He has a lot of hours of lectures here. I recommend you watch them, but I'm not going to require you to watch them because it's kind of a lot more than the typical kind of 2 lectures a week worth of material. But I'll post the corresponding links to that also here. And so you'll see over time this lecture notes and videos will grow as I add more lectures. So as I said, I'll post the PDF, I'll post Dr. Lemus's videos. Office hours are kind of already gone over. So weekly quiz problems. So the graded problems, I'm not going to grade all of the like a whole bunch of homework problems every week. Every week I'm going to post one what I'm going to call a quiz problem. It's going to be one fairly short problem, kind of a quiz-like feeling, typically 1 page. And I'm going to post them on Thursday. They'll be due the following Thursday at 11:59 p.m. EST. And I'm going to grade it. In total, that will be 20% of your grade. There are going to be about 12 of them. If you look at the outline for the course, I think I have right now about 12 of them listed. So I'm not sure we're going to get to all 12, but ideally we'd have 12 of these. And what I'm going to do is I'm going to drop the lowest 2. So your grade will be the kind of average, that 20%, but the average grade for the your best 10 out of those 12 quiz problems. That gives you some leeway so that if you kind of stumble once or twice, it doesn't kill you, but you do need to do them. And you're going to submit these on Blackboard. Don't email them to me. There's a lot of students in this class that will just swamp my email. and I won't accept any late submissions unless you kind of have a good excuse and you come to me in a reasonably in advance for it. Additionally, I'm going to post some suggested problems. So if we go back to the website here, I have a section for quiz problems. So this is a quiz problem for first week. Here's the link. Here's the due date. So if I click on this, let's open that up. So here's the first quiz problem, due August 27th. Short little problem, space to write your answer below. And this is also posted as an assignment on Blackboard, which we'll take a look at. So you write it, you'll take a picture or scan it, upload it. And that will be kind of your grade for the week, and make sure you're keeping on top of the material. Additionally, I'm going to post a bunch of suggested problems. So here, 820, SP1, suggested problem 1, suggested reading, Lima section 1.3, and here are the suggested problems, chapter 1, 63, 4, 69, 70, 73. Not going to grade those. What I'm going to do is on Blackboard, I'm going to post the solutions to these. So what you can do is you can do them, you can check your answers against my answers, come talk to me in office hours, and then you'll have to do the additional kind of one graded quiz problem, but besides, I'm not going to grade all of the kind of, I'm going to typically post about 10 per week suggested problems, but they're going to be quite important because if you don't really do and follow along with the suggested problems, it's going to be really hard to kind of stay on top of the material if you're just doing the one quiz problem a week. So they're suggested in so much as they're not graded, but I think it would be quite hard to do well in the course if you're not going to follow along and try and do this problem. So, this is a senior level class, so I'm not going to grade every single scrap of work. Okay, so this is kind of the website, and this is kind of our home page here. The other site is, of course, Blackboard. Let's see if this thing loads. So here's our Blackboard page. And there's a link here on the left to the web page. Okay. And then there's, if you go into assignments, assuming that wants to load, here we go. This is QP1, quiz problem 1. Here's a link to the PDF quiz problem 1 due date. So I can click on it. And there'll be a submission spot for it. So I'm going to upload my answer here, right? Sure you're all familiar with that. Upload my file, submit it by the due date to get full credit for it. Additionally, on the Blackboard, I will post solutions for the suggested problems. I'm not going to post them on the main website just to kind of control them a little bit, but I'll post those solutions for the suggested problems there and solutions for the quiz problem after it's due. Okay. I think that's enough administrative stuff for now. So that's basically the deal for the course. Feel free to email me if there are questions about any of this. But other than that, let's get on to the actual topic of probability, which is a fun and exciting topic. So let's close this out. Okay. So, lecture 1. We're going to do kind of a review of some basic set notation. So this is definitely a bit of a review, but it'll be a nice kind of easy way of getting into the material here. This set notation, as we'll see, is going to be really important for when we start off in probability and kind of axiomatically build up a kind of real definition of what probability is. So we're going to start with let's see if we can start. This is going to load here. So we're going to start off our discussion of kind of basic set notation by giving a kind of heuristic definition of a set. And their definition is going to be that a set is just a collection of objects. So examples being, I can have the set S be the set numbers 1, 2, 3, denote that as 1, 2, 3 between my curly braces. I could have the set, say, blackboard bold N, which is my natural numbers, which is 1, 2, 3, 4, etc., all the way out ad infinitum. So this is what's called the natural or counting numbers. So basically positive integers. I could have a set blackboard bold Q, which is m over n, where m and n are natural numbers. So this is basically the rational numbers, right? Or something akin to that. Another definition, once we define kind of what a set is that we have the definition of set membership. So we say, quote, some element X is in a set S, denoted X in S, if our set S contains X as an element. So examples of this, of course, we could say that 5 is in the natural numbers n, all right, because this natural numbers is, of course, 1, 2, 3, 4, 5, 6, etc. And here we go. 5 is an element of n. So 5 is in n. Other things we could say is that, say, 2/3 is in Q, as defined above. 2/3 is a rational number. And we could also say 2/3, well, is 2/3 a natural number? No. And so we could cross out, that's a little big of a cross out, we could cross out the containment symbol, that kind of backwards U thing, say, and this is read as, quote, not in. So you would read this as 2/3 is not in the natural numbers. Okay, so basic set membership. Of course, once we define set membership, we can define containment of sets. And so we say that, quote, A is a subset of another set B. So set A is a subset of another set B, denoted A backward C thing B. That is A is a subset of B. And this is a definition. We say that A is a subset of B if X being an A implies that X is in B. So one very useful thing, not only for this basic set theory, but as we'll see next lecture, generally for kind of basic probability statements, is the use of Venn diagrams. So here's kind of my universe of sets. I have some set A, and we denote that A is a subset of B if B is bigger or contains A. And why do we say that A is a subset of B? Because if I pick any little x that's in A, it's definitely contained in the circle A. That implies that it's contained in the circle B. So any little x I choose in A, since A is kind of contained in B, that is A is a subset of B, it must be in B. The converse isn't true. We can find points, say over here, in B that aren't in A. So B is not a subset of A. So you could even say, example, given this picture, A is a subset of B, but B not, oops, a little big, is not a subset of A. So this kind of little proof is nice for giving you intuition about what's going on, drawing a little picture like this. It doesn't really constitute a proof per se, though. This would not be enough for an exam or a homework. You really have to do kind of more like a Math 214 kind of proof to show something. But dead useful for getting intuition about things. Okay. So that's set containment. We can look at some other examples of set containment. Of course, the set containing numbers 1, 2, and 3 is a subset of the natural numbers. The rational numbers is a subset of the real numbers. So these are the real numbers. Don't ask me to define that. That's an analysis question for an analysis class. But of course, the natural numbers is not a subset, of course, of the set 1, 2, and 3. Let's draw like that. Okay. So 1, 2, 3 is a subset of n because 1 is an n, 2 is an n, 3 is an n. If any element of the set 1, 2, 3 is also an n. So if you're in the set, you're an n. Every rational number is a real number, not the other way around. Pi is a real number, not a rational. And conversely, as I said, there are natural numbers that aren't 1, 2, and 3. Okay. So that's set containment, or subset. From that allows us to define what we call set equality. And the kind of obvious definition of set equality is that two sets are equal if they have the same elements. More formally, we say quote, A is equal to B, so subset A is equal to some other set B if both A is a subset of B and B is a subset of A. So they contain each other. In this case, we write, quote, A equals sign B. So that's the formal definition, is that they contain each other. Of course, if they contain each other, then they must have the same elements, because every element of set, if A is a subset of B, every element that's in A is in B, and if B is a subset of A, every element that is in B is in A. The only way this happens is if they have the same elements. We've actually already used this definition, where I wrote things like n is equal to 1, 2, 3, 4, etc. So we kind of already cheated here. It's a little bit circular, but that's the formal way to define it. And so if you want to prove that two sets are equal, which is something we're going to want to do in this class quite often, you got to show they contain each other. Okay. So those are kind of real basic definitions for set notation. We then get on to operations that we can do for sets. So this is the kind of next section of set operations. Okay, so what operations can we do with sets? Well, the most basic operation we can do with sets is set union. So the union of a set A and a set B, denoted, quote, A cup B, or looks like a U B. This is defined as, so A union B is a new set. It takes two sets and it combines them into a new set. So the set A union B is defined to be the set of all x, and then we're going to say x such that, so the bar is read as such that, x such that x is in A or x is in B. Great. So our definition of union is basically the union of two sets is the combination, is everything that's in one or the other. So it's you see the operational OR here, right? So it's basically the set equivalent of the logical operation OR. So we can draw a little picture or draw a Venn diagram of this, which is a really handy thing to do at the beginning of the class here. If I have one set A and I have another set B, then my set A union B, I'm going to kind of shade in green here. So that here is the set A union B. It's everything that's an A or B. So we can look at some examples here. If A is, let's say, the natural numbers, so that was 1, 2, 3, 4, all the positive integers, and B is equal to the negative integers, so -1, -2, -3, etc. A union B is, well, I'm going to write it this way, the set of positive or negative integers, plus or minus 1, plus or minus 2, plus or minus 3, etc. Notice there's no 0 in here, as it happens. More examples. If we take the rational numbers Q and union them with the real numbers, what do we get? We're going to get back, just the real numbers. Why? Because, as we said above, the rational numbers, Q, is a subset of the real numbers. So there's a little theorem here you can think about. More generalizing kind of this concept. But so the rational numbers are all real numbers. So it's either a rational number or it's a real number. Well, if it's a rational number, it's already a real number. So we don't actually get anything by unioning on the rationals, right? So the more general fact is that if A is a subset of B, then if we look at A union B, it's always just going to give us the bigger set. And the kind of picture proof that you should have in the back of your mind is that if A is a subset of B, so that's our set B, here's our smaller set A, the union is kind of all of either of them. So if we kind of highlight that here in green, it's just the bigger set B. Okay. Other examples that we could look at. If we take the natural numbers and we union them with the natural numbers, what do we get? We're just going to get back the natural numbers. This is actually follows from this fact here. Any subset is a set. Any set is a subset of itself by equality. A set is equal to itself. Okay, that's kind of what we mean by equality. And so it's a subset of itself. So by this fact, if we union it with itself, we're just going to get itself back. So this is often called idempotency. It's a useful fact. We union A, kind of the more general fact here is that if we take any set A and we union it with itself, we just get itself back. Okay. So that's one of the two basic set operations, being union. The second basic set operation is intersection. Okay? And we define the intersection of two sets, A and B, as, so our notation is it's going to be A upside down U, or cap B, is the intersection of A and B, is defined as all x such that x is in A and x is in B. So it's the same definition as union, but we're switching the or for an and. So it's the set equivalent of the logical and. So A intersect B, A cap B. Oftentimes we're going to denote this, and I will in this course denote this as just writing them next to each other. A, B. That is everything in A and everything in B. So if we were to draw a Venn diagram of this, and we have two sets, we have a set A, we have a set B. The intersection is the overlap. So it's everything that's in A and everything that's in B. So this overlap here is what I'm going to call AB, is A intersect B. Now you might not have seen this notation where I just write A kind of A times B or AB next to each other. We're going to see why that notation is really kind of helpful in the probability class and why probabilists like to write it that way. So examples of intersection. If we take, again, A to be the natural numbers and B to be the negative integers, -1, -2, -3, etc. It's supposed to be a 3 here. Ooh, that does not look like a 3. Let's try that. -3, okay. Right? If we look at AB, the intersection of A and B is what? Well, of course, they don't share anything, actually. They have no common elements. So their intersection is empty, as we say. Or the intersection is the empty set. So this is called the empty set. This is a very important set in probability. It's the set that has no elements. Other examples are if we take the rational numbers and we intersect them with the natural numbers, what do we get? The rational numbers are all the ratios, natural numbers are the counting numbers. We take the intersection, what do we get? We're actually just going to get back the counting numbers. Why? This follows because, again, the natural numbers is a subset of the rational numbers. So as we saw before, if we take the union of subsets, we get back the bigger set. And if we take the intersection, we get back the smaller set. And again, there's kind of a more general fact or theorem that if A is a subset of B, then the intersection AB gives us the smaller set, A. And the kind of quote proof, or the little picture that you should have in your mind here for this fact, of course, here is my bigger set B, here is my smaller set A. Intersection is all the places that these two sets overlap. They overlap identically with the smaller set, and so that's what we get when we take the intersection of two sets like this. Okay, so these are the two basic set operations, union and intersection, and we're going to be using them quite a lot. I guess the other last fact we could say, there's an idempotency law for intersection, which is that if I take a set A and I intersect it with itself, I'm also going to get back itself. So just like we had with unions, that's true of intersections also. Okay. So other useful definitions that we can now, in operations we can do with sets, one of them that we'll be seeing is called set difference. And basically allows us to kind of subtract two sets, as it were. So we say that the difference between two sets, A and B, denoted over A, and we're going to kind of write, I mean, what you'd like to write is A minus B, I suppose you could. Typically, it's written with kind of a slanty minus sign. So it's written as A less B, or A, what's that? Slash B. And this is defined basically as everything that's going to be in A. So A less B is defined as everything, all x's, where x is in A, but x is not in B. So if we were to draw this out with a Venn diagram, we have, let's say, two sets, A and B. We want A less B. It's everything in A, but that part that's in B. So kind of shaded everything in A that's not in B. So we exclude kind of the middle intersection here. So examples, if we want to look at some examples, if we have A, set 1, 2, 3, B is a set 3, 4, 5. You could look at, say, A less B, which is everything in A that's not in B, which is just the elements 1 and 2. You could similarly look at B less A, which is everything in B that's not in A, which is 4 and 5. So order really matters here, as is common with subtraction. And so A less B is not the same as B less A. Other useful operations that we can do. Another real basic definition is set complementation. So set complement. So typically the way people will define set complementation. So here's what we want to do. We want to say that the complement of a set, let's say A superscript C, so a complement, is the set of everything that's not in A. So it's everything, it's the complement of A. It's everything that's not in A. Unfortunately, this is a little bit ill-posed. In spirit, it's the right thing to do, but it's a little bit ill-posed. What else is not in my set A? Well, there are lots of things not in my set A. We need to define the complement with kind of respect to some universe. So oftentimes the universe is kind of implicit, but what we really need is we need some universe set. Let's call it big S. We'll see why S next time. And our set A is going to be some subset of S. So our universe is basically the collection of all the some set that contains all the possible sets we're going to look at. So there's a bunch of possible sets in here containing things. One of them is our set A. And we want to look at a complement. And so the proper way to define a complement is that a complement is going to be S minus A. That is, it's everything in S such that it is not in A. Now that's a well-defined complement because we know what elements are in the complement. If we don't kind of define it in relation to a universal set kind of containing everything, we don't really have any idea of what you mean by things not in A. There's lots of things not in A. What's the kind of universe of possibilities of things that are not in A? So this is our real definition. And notice that you use a set difference. But in spirit, people don't tend to always refer to the universal set A. It's kind of understood what the universe is. And so people will just write something like what we wrote up here, which is everything that's not in A. So in our Venn diagram, if this is our set A here, let's just highlight that in red. This is our set A. A complement is, of course, everything not in A. So this here is a complement. So A with a superscript C. And we can cook up some examples. I'm sure you can cook up some examples. example, let's say A is the set 5 and 6. The universe of sets is going to be the natural numbers, so A is definitely a subset of the universe. A lives in that universal set S, right? So note here that A is a subset of S. Then a complement, that is the complement of A with respect to S, which is probably the more proper way to say it, is everything in S that's not in A. So 1, 2, 3, 4, not 5 and 6, 7, 8, etc. Notice that this really shows why we need this to kind of define what our universe S is. If I didn't say what the universe of possibilities were, I wouldn't know. Maybe 1.2 could be in there. Pi. Is pi in the complement? Well, if we don't have a kind of universe, we don't know what the possibilities are. But if I say my only possibilities are natural numbers, well, these are the only natural numbers not in A. Okay, well defined. Good. Set complementation is super important probability. And that's one of our real basic set operations. Okay. So those are kind of really simple set operations. There are a lot of theorems about set operations, and I'm sure you've seen some of them before, and we'll see kind of how to use them in probability and how they're useful for probability. I'm just going to write down some basic theorems. So here are some basic theorems. And I'm not really going to go through and prove these. These are kind of basic. You'll prove maybe some of these in the homework problems and the quiz problem this week and some of the suggested problems. But we're not going to go through all these. But some of the basic kind of rules of the game. Commutativity. That is, we can commute sets under certain operations. So A union B is the same thing as B union A. So commutativity means we can switch the order, or we can commute A and B. AB is the same as BA. So the order doesn't matter for those. Other theorems, properties. Nope. Let's see if we can draw a circle here. Associativity means I can draw my parentheses wherever I want. So A union B union C is, I could change where my parens are without a penalty. That is the same thing as A union B union C, and that's true for intersection. A intersection B intersection C is the same thing as A intersection B intersect C. There's also a distributivity law. And how intersection and union interact with each other. There's a couple ways of writing this, or a couple forms of it. If I look at A intersect B union C, I can distribute my intersection across the union. This is AB union AC. And I can also do the same thing switching intersection union. If I have A union B intersect C, I can distribute my union across the intersection. This is A union B intersect A union C. So I can distribute things nicely in that way. The fourth is basically a logical law called De Morgan's law. Invented by a guy named De Morgan, who made some basic contributions to probability. And De Morgan's law talks about how, has basically two parts. Part I is how I can distribute complements over unions. So if I have A union B, and I want to take the complement of that, what you like to be able to say is that, well, this is A complement union B complement. But actually I have to switch the union for an intersection. So A union B complement is A complement intersection B complement. And the second part of it tells me how I can distribute complements over intersections. A intersect B complement is A complement union B complement. So that's De Morgan's law. Very useful, again, for distributing complements over unions and intersections. Okay. So these are the basic kind of rules about the basic set operations. But we can also kind of expand things and talk about infinite or countably infinite in this course. Infinite versions of the set operations. So, okay. First, we're going to say we're going to have a collection of sets, and our collection is going to be, let's see if this is going to give me a different color here. A1, A2, A3, and so forth. So potentially a countably infinite number of these sets. They're going to be subsets of some universal set S. So another way we can denote this is this collection of sets. I'm going to write, let's write it this way. Bracket A sub I goes 1 to infinity. Okay, so it's an ordered collection of sets of these A sub I. Now, if we had two sets, we could define union of two sets. And we could kind of iteratively take the union of these. But what if I want to take the union of all of them? The union of these sets, let's write union correctly, denoted, so our notation here is going to be a big U, I goes 1 to infinity by A sub I. So it's like a union, it's like a infinite sum, but it's an infinite union of all the A sub I. This is defined to be what? So what's union? Union is the collection of all of them. It's kind of like a summation. In fact, next time we'll see really how union is kind of a summation for probabilities. But it's kind of like the summation of all the sets. It's the set that contains everything that's in potentially any of these sets. So the infinite union is any element of my universe such that X is an element of one of these A sub I. So X is an A sub I for some I. That's one way of writing it. Another way of thinking about it is X is in at least one A sub I. Or there exists an A sub I where X is in an element of it. The picture you can think of, so our Venn diagrams can be useful here. Though I'm not going to be able to draw an infinite number of sets, you have some collection of sets, A1, A2, A3, A4, etc. The union of all of these is just the stuff that's in all of them. So it's kind of the combined shaded region, an infinitely of the infinite number of sets. So that's our definition of an infinite union. And there are analogous properties of these unions. One of them is the quiz problem for this week. But we can look at, say, an example of this. Let's look at an example. This might be illustrative. So our universe of sets is going to be the half-open interval from 0 to 1. So this, if I have my number line here going from 0 to 1, it's a set that doesn't include 0, but does include everything up to and including 1. Okay. And if I define a sub I, I'm going to define this to be the closed interval from 1 over I to 1, including 1 over I and 1. And I'm going to do this, define this for each I, 1, 2, 3, etc. So what are some examples of this? A sub 1 is 1 over 1 to 1. It's actually just a set that includes 1. A sub 2 is the set from 1/2 to 1, including 1/2 and 1. And I'm sure you can figure out the rest of the pattern. A sub 3 is the set 1/3 to 1. So if I were to kind of draw these on the number line, here is 0, here is 1. A sub 1 is just kind of the point 1. A sub 2 goes, so this is kind of A sub 2. A sub 3 is even bigger, it goes from 1/3. This gives me A sub 3. It's a little bit sloppy there. Let's see if I can write that better. A sub 3. Okay. Right, and so furthermore, A sub 4 goes 1/4 to 1, A sub 5 goes 1/5 to 1, etc. So you can see the sets are getting bigger and bigger and bigger, and they're kind of the lower end here is creeping towards 0. So here's a question. What is my infinite union of these A sub i's? So the infinite union is the set of elements that is in at least one of these. So it's kind of the collective set of these. The answer is that it is actually the whole universe. 0 to 1, not including 0, but including 1. So that is our universal set S. Why is that true? Well, if I take any number in this interval, so I take any number I want, say some number here, the question is that in our union? The answer is yes. It is in our union because there is some set, for example, it looks like A sub 3 includes that point. So that point is in A sub 3 is in the union, therefore that point is in our union. I could pick another point further down here. Well, it looks like now that one's included in A sub 4, but that's still included in our union. In fact, I could pick any point I want, even as close as I want to 0. There's going to be some set that's large enough that it's going to include that point, and therefore it's going to be in our union. That works for any point that is bigger than 0. 0 won't be, because 0 is actually in none of our sets. So that's why we don't include 0 in our interval, but we do include 1. 1 is obviously in every single one of them. And so our infinite union is this set, 0 to 1. Okay. So that's infinite unions. We correspondingly, you can define an infinite intersection. So let's write out that definition here. Come on, pen. Let's try this. Infinite intersection. Okay. So we define the infinite intersection of a collection of sets a sub I goes 1 to infinity. And our notation denoted is now a big cap or big intersection, I goes 1 to infinity, of the a sub I. And just like intersection is kind of a dual to union, infinite intersection is kind of dual to the infinite union. That is, the infinite intersection of all sets. Well, the intersection of two sets is the set is the kind of elements, the set containing the elements that's in all of them. So the infinite intersection is everything in my universe such that that element is in every a sub I. Is an a sub I, we could say for all I. Or for all I, a sub I, or x is an a sub I, or x is in every a sub I. Well, multiple ways of saying it. So that's our definition of infinite intersection. And kind of the Venn diagram that we can draw for infinite intersection here is that if I have some collection of sets, let's say I have some A1, and then inside that maybe I have an A2, and inside that I have an A3, and they kind of spiral down, dot, 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 dot. The infinite intersection is going to be whatever kind of the core set is that's contained in all of them. So that's going to be my, oops, not union, but intersection of my a sub I. Okay. So example, if we take the previous a sub I from the previous example, where a sub I is the set 1 over I to 1, then I can ask you, what is the infinite intersection of all these a sub I? So it's the collection of elements that are in each of these a sub I. So what is the collection of elements that are in each of these a sub I? Well, if I take any, as we said before, certainly the number 1 is in all of them, right? Because they all contain 1 as their upper bound. But if I take any other number less than 1, it's not going to be in my infinite intersection because it's not in every single one. For example, if I take the number, let's say 1/4, well, that's not in a sub 2 because a sub 2 goes 1/2 to 1. And if I take the number 1/3, that's also not in a sub 2. If I take the number 1/5, that's going to be in a sub 5, a sub 6, a sub 7, but it won't be in a sub 4, a sub 3. So actually the only element that's in all of these sets is the number 1. And so the infinite intersection is just going to be the number 1 in this case. So sometimes these infinite intersections can be a little bit counterintuitive, but we will use them extensively in probability. And so it's good to become familiar with them. Okay. So another useful definition when we're talking about collections of sets is disjointedness. So we say that two sets, A and B, are disjoint if their intersection is empty. So the intersection of A and B is the empty set. That is, they share no common elements. So the Venn diagram for this is really simple. It's just two sets that don't overlap. Oops. So here's my set A. And if I can draw a circle correctly, we can draw set B. There we go. They don't overlap. So let's say no overlap. That is not writing well. Let's try that again. Overlap. Well, I tried. Okay, so let's look at some examples of this. If I have a set A, and my set A is going to be just the number is 1, 2, and 3. And I could have a set B, and B is going to be the numbers 4, 5, 6. Then these two sets are disjoint. Why? They share no common elements. That is, AB, the intersection of A and B, is empty. So disjointedness is defined for two sets. And of course, we can define a similar concept for more than two sets. And that is what we call pairwise disjoint. So let's say here, that our definition, pairwise disjoint, so if we have a collection of sets, A sub I goes 1 to infinity, we say they are pairwise disjoint if pairwise the collection is disjoint. That is, A sub I intersect A sub j is empty for all I not equal to j. That is, if I pick any two sets, A sub I and A sub j, as long as they're not the same thing, sets are not typically disjoint from themselves, except the empty set. If we pick any two sets, they're disjoint. That is, their intersection is empty. So an example here of pairwise disjointedness is, let's have the set A sub I be the half-open interval I to I plus 1. So here's my number line. So this goes for I, goes 1, 1, 2, 3, and so forth. So A sub 1 goes from 1 to 2, not including 2. A sub 2 goes 2 to 3, not including 3. A sub 3 goes 3 to 4, etc., not including 4. And these are pairwise disjoint. Okay. That's our definition of pairwise disjointedness. It will be a very useful definition. Our second to last definition is a partition. This is something that people may or may not have come across. And a partition of a set is basically if we break apart a set into some non-overlapping subsets. So, okay. Let's say given some universal set S and a sequence of sets A sub I. It could be an infinite sequence. Hell, let's just be vague. Some sequence A sub I, we don't know. It could be an infinite sequence, could be a finite sequence, doesn't really matter. And each of these A sub I are a subset of S. Then we say that the collection, these A sub I, are a partition of S if two conditions hold. And those two conditions are, one, that the set of A sub I are pairwise. Oftentimes we leave off the adjective pairwise. We just say that a collection is disjoint. So you're kind of pairwise, disjoint. So they don't overlap. And two, if we look at the union, it must be a little vague about what the indices of our union is. The union of these A sub I, so I'm just going to write it like that. It could be infinite, could be finite. The union of all these things gives us back the set. So our partition is a kind of breaking apart of S into non-overlapping subsets that, when we put them back together again through a union, give us back the original set. So the nice picture you should have in your mind, Venn diagram, is this whole blue box is going to be my universal set S. We're basically just going to break it up into some partition. A1, A2, maybe this is A3, over here is A4, and maybe this is A5. So there's a 5-set partition of a set S. So none of these sets overlap, that is, they're disjoint, pairwise. But if I put them all together again, I get Humpty Dumpty. I get my set S back. So meets two conditions, that is a partition. So the example from above, if I take those previous A sub i's, which were what? They were I to I plus 1, not including I plus 1. Then these, they partition what? Well, any collection of disjoint sets. So they're disjoint. You should convince yourself they're disjoint. We said that last time. These are disjoint. Any set of disjoint sets, any collection of disjoint sets, always partition whatever their union is. So they certainly partition the numbers 1 to infinity. So there's kind of half-open intervals starting at 1, which we call S. So they partition that set. Cool. Cool. So our last definition for the day is going to be of a power set. Definition of a power set. And a power set is just the set containing all subsets. So for a set A, the power set of A, and I'm going to denote this two ways. So denoted either P of A, or alternatively, sometimes people would denote it as 2 to the A. This is where we get the term power from. And we'll talk about that notation real briefly. The power set of a set is the collection of all sets B that are subsets of A. So it's the collection of all subsets of A. So example being that if A is the set 1 and 2, then the power set of A, 2 to the A, is the collection of all subsets of A. What are the subsets of A? Well, the set containing just the element 1 is a subset of A. The set containing just the element 2 is a subset of A. So those are the proper subsets. Of course, the set itself, A, which we could just write as A, is always a subset of itself. And what's always a subset of every set? The empty set. So the empty set, that's supposed to be is 0. Oh boy. The empty set here is a subset of every set. So our notation, we can say notice that if we look at the size of A, so this is cardinality, the number of elements in a power set. The number of elements in the power set is 2 to the number of elements in the set. And that's where we get our notation from. So this is also where we get the term power set from, is that the number of elements in the power set is the power of is 2 to the power how many elements are in a set. So the power set is again going to be very kind of integral to our study of probability. So it's a nice little review there. Okay. So today we've reviewed some basic set notation. Hopefully most of this is kind of familiar to you. And this is going to set up really nice next time for kind of axiomatically studying probability. So if any of these concepts are unfamiliar, I suggest reviewing them. Our first kind of suggested problems and quiz problem that I'm going to post today are going to be on this stuff. And next time,